Okay, so here's an example problem for energy levels. I've got this ground state for a gas where it's 10 EVs. That's n equals 1. That's its first state. And then I've got the other states listed up here. A photon comes in of exactly 25 EVs. With 25 EVs, that's 10 plus 25. So that's going to push this electron all the way up to an excited state of 35 EVs. So the ground state is where it's stable, and the ground state's where it wants to stay, but this one's excited. Now, usually the photon disappears because it's absorbed by the electron, but I'm going to leave it here on the diagram just to remind you of what happened. If the photon had been 32 EVs, nothing would have happened. If it had been 22 EVs, nothing would have happened. It's got to be enough to add up to one of these energy levels, or in this case, 25 EVs. So here it is at the excited state, and it wants to get back to the ground state. And to do that, what it's going to do is it's going to take two jumps down. The first jump is going to go down to n equals 2, and as it loses energy, it's got to give it away, so that's going to be the photon you just saw leaving. And the second one's going to go down to n equals 1, back down to stable state, and again, if it loses energy, it's got to give it away, so that's going to be the photon. So here's the question. What frequency of electromagnetic radiation is absorbed by the gas, and which frequencies of light are emitted or is emitted by the gas? So absorbed. Remember when the photon first came in, the electron absorbed it, and then it added that 25 EVs to it. So the energy absorbed is equal to HF. The frequency is equal to the energy absorbed divided by Planck's constant. So F is the energy 25 EVs converted to joules divided by Planck's constant, and that gets me 6.03 times 10 to the 15 hertz. Okay, next part of the question. When the electron jumps down from an excited state to a less excited state, it has to lose energy. So it emits a photon to do that. So the emitted energy is equal to HF. So this time, instead of absorbed, I'm just calling it the emitted energy. F is equal to E over H. That's emitted energy over H. And it's going to be 35 minus 20 EVs, because it's not the whole thing. It's just the part that it did the transition from N4 to N2. Convert that to joules, divide by Planck's constant, and that's 3.62 times 10 to the 15. Now, it's going to do it one more time. The next time it's trying to get down to the ground state, so it's going to emit another photon, and this time when it emits the photon, E is equal to HF, again, F is equal to the emitted energy over the H, F is equal to 20 minus 10, it's the jump that it made, times Planck's constant, divided by, time converged over to joules, then divided by Planck's constant. And when I do all that, I get 2.41 times 10 to the 15 hertz. So all this is going on, and we can't even see it with our human eyes because the frequency is too high.